So, good afternoon everyone, and welcome to this session where we're going to talk about the fact-based realities of AI-assisted coding. And we're going to cover both the good parts, the bad parts, as well as the slightly ugly parts of it. And we're going to start all the way back in 1977. Because quite recently, I got exposed to the promises of AI and AI-assisted coding in a very unexpected way. So earlier this year, I started a new hobby. I wanted to write games for this machine. Has anyone ever seen that machine before? Wow, that's a lot of you. That's actually quite surprising. It's an Atari 2600, right, from the 1970s. So I started to learn to code for this machine, and I have to admit, it's probably one of the hardest things I've ever done. Because that machine, first of all, it lacks an operating system, meaning you have to do everything on your own. Second, and believe this or not, that machine comes with a full 128 bytes of memory, right? The good news are you're compensated for that by having a full 4K of read-only memory. The bad news are that you have to use that not only for your game logic, but also for all graphics and sounds. So I really struggle with this, I have to admit that. But at some point, I managed to wrap up my first game, really proud, and I pushed it to GitHub. And then I got to see this ad, where GitHub claimed I could become 55% faster on my hobby. And at first I thought, this is interesting, right? So you get all these existential questions and thoughts, like, do I really want to become quicker at my hobby, right? Should I take on another hobby then, or what do I do with that time? And then I start to think, 55% faster at what, right? So let me ask you, how many of you have seen this claim of 55% faster? So that's like a large portion of the room. How many of you, keep your hand up if you have read the research paper that that claim is based on? Not so many, just a few hands. So let's go through it together. So I have to say that this paper, it's actually a very good piece of research. I like it. Because like all good research, it's very clear about its limitations. And some of those limitations are highlighted here. And you don't have to read them because I'm going to kind of, try to simplify them a little bit. But first of all, what the researchers are very clear about when they studied this was that they did more or less a classroom task. And what they're very clear about is that this finding of 55% faster, which seems to be a genuine effect, they simply don't know, does it generalize to real programming tasks, right? We just don't know. Second, what they also found was that this 55% faster effect was something that was experienced by more junior and less experienced developers. So on one hand, that's a good thing because it probably means that maybe Gen AI can help newcomers to programming to kind of grow into the field a little bit quicker. That's a generally good thing. On the other hand, if you're a more experienced developer, you're probably not going to experience that speed up, right? But finally, and what I want to focus today's talk on is the last bullet here that says that this study does not examine the effects of AI on code quality. So that's kind of interesting. Is code quality important? More specifically, if we become faster and we can produce more code faster, what are the implications of that? What does it mean for us as software developers, and what does it mean for the industry? And I like to think that there are two sides to this. There's first the very human side, and then there's the financial side. And I want us to look at both of them. So first of all, the human side. And I really do love this quote by Kevlin here, where he says that we have all turned ourselves into maintenance programmers. Because after all, the reason I went into programming, the reason I picked up a hobby on coding on that old Atari machine is because I really love the problem-solving aspect of programming, right? That's the fun and creative part. And with Gen AI, we're basically taking that part, outsourcing it to the machine, and leave ourselves in the position of maintenance programmers. That is, we have to understand the code that someone else wrote, in this case, a machine. So that's something I think we should all really consider. But there's much more to it. Because 55% faster, again, at what? At writing new code. If we look at what we as developers actually do, we see something very, very interesting. Because writing new code is a very small part of our day job. It's 5%. 5% of a week is spent writing new code. The majority of our time is spent trying to understand the existing code. That's 70%. And yet, what we do today is that we're focusing AI on the small part, right? Writing new code. Whereas the big win is obviously the 70%. Now, 55% faster at writing new code. That translates roughly into 1 extra hour per work week. And 1 extra hour, that's good, right? I mean, if I get 1 extra hour, I can spend more time with my Atari 2600. So it's a valuable thing, but it's still just 1 hour. So it's not particularly groundbreaking, not particularly disruptive. If we want to be really disruptive, we need to focus on the big 70%. So what stands between us and code that's easy to understand? Because if we can optimize code for understanding, then we can indeed become much quicker. As always, it's complexity, accidental complexity. That is code which is more complicated than what the problem calls for. And there is this absolutely wonderful quote by Deming here, where he says that a bad system will beat a good person every time. Ever heard that? I really love that quote, right? Because when we accelerate the pace of coding, I mean, we can always write more tests, we can always fire up a debugger to try to understand some code, but as the system scales up, this is going to be virtually impossible for a single individual. So I like to claim that with the acceleration that AI enables, code quality is going to become even more important, right? Its importance is going to grow all the time. And the reason I say this is because over the next decade, we're going to be in a hybrid model where we as humans have to understand code that's written by machines. And that's going to be a really, really expensive phase unless we pay extra attention to code quality. So what I want us to do now over the next 5 minutes is to dive a little bit deeper into code quality and try to understand it, what it actually is, how we can measure it. And then we're going to look at if generative AI can help us with code quality. Sounds good? Perfect. You don't have much choice, so here we go. So, first of all, code quality is fascinating because I have been in the software industry for almost 30 years now. I worked with so many different companies, and every single one of them have claimed that code quality is important. And yet, no one ever had any numbers to show me that, right? No one could ever support that statement with numbers. And I think that is telling, because what I also observed is that as soon as something hits the fan, and that something is usually a tight deadline, the first thing that flies out of the window, what is that? Code quality, right? So we're paying lip service to it. And a couple of years ago, me and a colleague, Dr. Marcus Borg, we wanted to change this perception of code quality. We wanted to be able to actually put some kind of metrics on top of it that shows how relevant code quality is to the business. So we decided to study the topic. And we published a research paper called the Code Red Paper, The Business Impact of Code Quality. And I just want to give you a quick summary of what we found there. So in this particular study, what we did was that we collected data from 39 companies. Each one of them had multiple commercial code bases. So this was a study on closed source code. So we basically measured the code quality at a file level. I'm going to talk about what we used as a metric in just a minute. But we also made sure in that study to include lots of different industry segments because we wanted to make sure that whatever we find is something that generalizes so that our findings are not specific to finance, telecom, or gaming, right? We wanted to make sure that it's a general finding about software in general. And for the same reason, we also included code in 14 different programming languages. So we have lots of Java code, C#, C++, JavaScript, all the usual suspects, right? So what we did was that we used the following metric as a proxy for code quality. So this is a metric that's called code health. So how many of you have heard about the code health metric before? Just a few hands. Okay, good. We're about to change that. So code health is a file level metric. And the way it works is that you take a file with source code and you parse it. and then you look for a bunch of different code smells. And these code smells, they can come at different levels. So they can be at the module level, function level, or the implementation level. And I just want to give you a high overview of what these are. So at the module level, you typically have code smells or design smells, or design problems like low cohesion. So is anyone familiar with low cohesion, what it means? So again, maybe 10% of the audience? Good, good. So low cohesion is basically when you have stuffed too many things, too many unrelated things into the same class, right? So maybe implement 10 business rules in the same class. What's the problem with that? Well, when it comes to understanding code, the problem is that you now have to understand 10 different things in order to make sense of just that class, right? So it's a barrier to understanding. It also opens up the risk for things like unexpected feature interactions, which are some of the worst bugs you can ever have. So low cohesion is a massive problem. However, just because you have a massive problem, that doesn't mean we cannot make it even worse. What we can do is that we can take a class with low cohesion, we can let it grow really, really large, and we can add something called a brain method to it. We have now created a brain class, right? And a brain method is something I promise all of you have seen it. It's a function that's ridiculously long. They're always really, really long because they contain so much logic. They're stuffed with conditional statements, so the logic is really tricky to reason about, right? And they do too many things. So the consequence is that the moment you want to change that particular module or class, you end up in the brain method, and over time they just become more and more complicated. Ever seen that? Yeah. So that's a function level smell. At the implementation level, we typically look at various complexity patterns. And one of them that I want to emphasize is what's called deep nested logic. So deep nested logic, what's that? Well, it's when you have an if statement inside another if statement, and then another if statement, and then maybe a for loop for good measure. That's deep nested logic. The reason it's problematic is because it puts a massive cognitive load on us as humans. It becomes really hard to reason about the code. And consequently, there's some very good research that shows that roughly 20% of all programmer mistakes are due to constructs like deep nested logic, right? So the way it works is that we scan the code for these design issues and code smells. There are 25 of them in total. Basically stick the probes into the code, pull them out and see what did we find. And then we have algorithms that can take the different findings, weight them together, and categorize every single piece of code as being in one out of 3 possible categories. So you can now have code that's either green, that's healthy code, that's where you want to be with most of your code. That's code that's fairly easy to understand. Then you have yellow code, which is problematic code. So this is code that's going to be challenging to understand. And if you're not careful, you might end up in the red category, which is, code that you never ever want to work with. So now that we know how to measure code quality, what we can do, of course, is that we can start to reason about whole systems. Because we can visualize a code base like this. It's a simple enclosure diagram. Every single circle represents a file with source code. And what I can do now is that I can very quickly see where are the strong parts of my application and where are the weak parts of my application, right? That might have technical debt and overly complicated code. So now that we know how to measure code quality, we need to know, what does this actually mean? What does it mean for code to be green or red in terms of a business impact? So this is why I want to present the results of that study. So does code quality matter to a business? What did we find? Short spoiler is yes, it matters. Otherwise it will be a very quick presentation. But what surprises me is how big the impact is. So what we did was that not only did we measure the code health of every single file, what we also did was that we connected to tools like Jira and Azure DevOps so that we can calculate information on how much development time was spent on each file depending on its code health, right? And what we found was the following. So if you have a green code, you can implement a feature twice as quick as someone that has red code. Is that on average? Is that something that's important to a business? Yeah, of course, right? Because it means that if your company has green code and my company has red code, and it takes us 2.5 months to implement something, you with the green code base can do the same thing in less than a month. It's going to be impossible for us to keep up. So green code is a competitive advantage. However, I was actually a bit surprised that the difference wasn't even bigger. So what we decided to do was to also look at the variation. So what we did, instead of looking at the average time to implement a feature, we looked at what's the longest it takes to implement a feature in each particular file. And then we tried to categorize that by code health. And what we found now is quite interesting. It turns out that there's a massive, massive risk associated with red code. Implementing a new feature or fixing a bug can take up to 10 times longer in red code compared to green code. Is that something that's important to a business? It should be massively important, right? So let me give you an example. So these days, I'm working as a CTO, and I always wonder what a CTO does, and now I know. What a CTO does is to make a lot of promises. So you might promise your sales team that, yeah, we're going to have this capability in a month. It's going to change everything, right? However, if we would have red code, I can make no such promise, because it could equally well take 9 or 10 months, right? And I would look bad, and I don't like that. If I instead take on my developer hat, because I still write a lot of code and I still enjoy it, then I also don't like red code, because red code is what's causing me stress, overtime, and missed deadlines. So red code is disastrous to a business. It's a massive uncertainty to the business. Now, one more thing. Since we had this, when we did this study, since we had this connection to Jira data and Azure data, what we could also do was that we could collect information on what type of work is being done. So is it new features or is it bug fixes? What is the team doing? And that means we could also correlate defect density to code health. And what we found here might be even more dramatic. It turns out that red code has on average 15 times more defects than green code. Could that potentially be important to a business? Of course, right? Of course that's important, because this basically translates into the product maturity perspective, right? So if you ship 15 times as many defects as your competition into production, guess what? Your customers are most likely not going to love you. And there's another aspect too, because what happens with all these defects that we ship into production? You know, just like in that old Stephen King book, they come back. And they come back in the shape of unplanned work. And unplanned work, as Jim Kim once told us, is the silent killer of all IT projects. And I've seen organizations that spend 60 to 70% of their time doing unplanned work, things they didn't anticipate, right? Things that broke in production. And you can imagine how incredibly challenging it is in those organizations to get anything done at all, right? Just a bunch of context switches and ad hoc work. So code health is important. Code quality is important. So how does this relate to AI? Well, I like to claim that we have set the stage now for something very promising. Because what this data basically tells us is that no, we shouldn't settle with just becoming 55% faster. That's nothing. We can actually become 10 times faster. And it sounds absolutely ridiculous until you actually look at the data. Because what this means to me is that we have a massive, massive opportunity. Because if we can take all that red code that we have out there and we can make it healthy, then that would actually allow us to accelerate in those parts of the software, right? Would allow to accelerate the whole business and produce fewer defects in the process. So I think this is even more important now that AI accelerates the creation of new code, because we want to make sure that whatever the AI spits out, we want to make sure that it's green, right? Otherwise, it's going to create a massive challenge for us. And the reason I know this is because we have done another follow-up study to the Code Red paper. So what we did was that we looked at onboarding times. How much longer does it take us to understand code depending on if it's green or yellow or red? So again, think about using an AI coding assistant. It would generate a lot of code to you. What happens if that code isn't green? Well, what happens is this, that you see on screen here, that unless you are the one who wrote that piece of code, it doesn't matter. You might already have domain expertise. We measure this on folks that already worked in a particular code base, right? So unless you're the one that wrote a piece of code, and you're now asked to do a small bug fix, like a one-line change, you're going to need 45% longer than the developer that wrote that code. If you're instead doing something larger, like a new feature, you're going to need almost twice the time to make that change compared to the person who wrote that code. So the way I view it is that this is a kind of a natural onboarding cost, an extra onboarding cost that comes with yellow and red code. So code quality is really important, because when we find ourselves in that constant onboarding mode, not only is it frustrating, it's also very, very expensive. So how can we take red code and make it green? The answer is, of course, refactoring, right? Optimize for software maintenance. So who is familiar with refactoring, the concept? So that's virtually a full house, very, very good. So I still want us to kind of agree on the basics here, because refactoring is simply the improvement of existing code without changing its behavior. And that sounds really, really simple, but when you look deeper, it's actually kind of constrained, because refactoring says that it's not a refactoring unless we actually improve the design. So again, that means that we need to have some kind of gold standard where we know that one piece of code is better, objectively better than another, right? Otherwise, it's not a refactoring. And second here, it's also not a refactoring unless we fail to preserve, or unless we preserve the behavior of the existing code, right? If we alter its behavior, we have introduced a bug. And I think that when we violate any one of these assumptions, I think that the technical term is a refactoring. How many have heard that term before? Cool, cool. We're learning some new stuff today. That's useful. So what we thought was that maybe we can kind of rethink how we use AI and put it to work on refactoring code, right? Taking red code and turning it green. And we did a research paper on this called Refactoring versus Refactoring. And what we did in that paper was that we simply took all the popular foundation models on the market, like OpenAI, Google's AI, Llama from Facebook, and we benchmarked them at how good are you at refactoring code. And as the gold standard, we used the code health metric that I showed you earlier, because it is the only code level metric with a proven business impact. So we wanted to make sure that when we get to refactoring, it's an objective improvement. So what do you think we found? How good of a job is the AI doing on the refactoring code? Well, let's jump right to the results. And there's a lot of data there, so I'm going to walk you through it slowly. So first of all, to your left, you see each one of the AI models that we used. And the first column simply checks how many of all the refactorings. We tried this with, we had a data lake with more than 100,000 examples on poorly written code with different code smells that I showed you before. And we simply asked the AI, please refactor this. And we put a lot of effort into the prompt engineering, so we wanted to get the best we could out of the AI. And what we found here is that the first column, valid code. So is the syntax valid? Is it code that we can compile at all? Turns out that the AI seems to be pretty optimized for that. Virtually all green scores, everything looks good. The first big drop-off comes in the second column, where it says code health improved. Remember, it's not a refactoring unless you improve the design. So here we lose roughly 30% of the solutions, right? The AI either makes the code worse or just changes it into something else without improving it. But the biggest drop-off is in the last column where it said valid refactoring. So what we did here was that we actually rerun the unit tests for each one of these refactored pieces of code and made sure they passed, right? So that was like our ground truth. And we see that the AI basically breaks the code in 2/3 of all refactoring attempts. The best performing AI only generates correct code in 37% of the cases. Does that look promising to you? Imagine that you had a colleague and they would break your system in 70% of all the changes they did. How happy would you be? My guess is that they would be asked to look for new challenges promptly. But when it comes to an AI, we seem to accept this level of performance. We call it hallucinations and everything is good, right? So at first, this looks pretty depressive, right? However, my team is made of optimists. So they basically looked at this data and said that, hey, yeah, but actually what this means is that it does the right thing in 37% of the cases. So if we could just find a way of finding those 37% good refactorings and separate out them from the rest, then we would be able to pay down 37% of all technical debt out there. That would be pretty useful, wouldn't it? So we set to work on this task. And what we quickly learned is that you cannot use an AI service out of the box. You have to do something around it. You have to build a safety net around the AI. So I want to walk you through the high-level architecture of the solution we came up with, and then we're going to look at how well it performs compared to what we saw before. So the way this works is that we built all of this using an IDE integration. So there's a plugin for it on Visual Studio Code. And the way it works is basically that you as a developer, you write some code. And you might have introduced some code smell or design issue. So now you ask the AI to refactor it. So you send a request. But instead of going directly to the AI services, we have something we call a model selector in between. The model selector is interesting because when we did this refactoring research, what we quickly found was that the AI is good at different things. So OpenAI might be better suited to some refactorings than Google, for example, whereas in other cases, Llama from Facebook might be the right choice. So what we did was that we basically trained a machine learning model to find the right AI for the job, right, for what the problem calls for. So here we delegate to one or more of these AIs and ask them, please refactor this code. And at some point, we get the proposal back. So we get some rewritten source code back. What we do now is that we do some fact checking on top of that response. So first of all, we run a code health analysis on it and make sure that, okay, is the code improving or not, right? And if it's improving, then we check, is this code still semantically equal to what we inputted before? If we fail any one of these quality gates, then we discard the solution as an incorrect solution, refactoring, right? If on the other hand, it passes both of these quality gates, then we send it over to the user and propose a better way of implementing that code. Sounds simple, doesn't it? Let's look at a couple of examples. Let's see it in real life. So what you have here is a piece of code. And you see in the plugin that we have here, it highlights which type of code smell that we have. But again, you don't really need a tool to tell you that this is deep nested logic, right? So again, deep nested logic, how can we refactor this? Well, let's try out the solution. So here's the prototype. So you see that next to that code smell, we have a small label that says auto refactor. So if I click on that one, what's happened, it went quickly, but what happened under the hood is that the request gets sent to the model selector, it selects an AI, we get the result, we fact check it, if it's good, we pass it on to a user. So now I see that the AI seems to have refactored my deeply nested logic by kind of modularizing the code a little bit more. So I can now inspect the code, and if I like it, I can simply just apply it, and my code smell is gone, and my code is now a little bit healthier. That was quick, wasn't it? Almost too quick. Let's look at another example. So this is another code smell. This is, you see that if statement, and inside it, you have something called a complex conditional. So complex conditional is simply when you chain together multiple conditions using logical operators like and or, right? Why is that a problem? Well, it's a problem because I, as a developer, when I see code like that, I mean, I can tell what it does. I mean, I understand the meaning of each one of these, but I have no idea why that code is there, right? I kind of lack the connection to the overall business problem I'm solving. So what we found out in that study is that the AI is actually quite good at a thing that we human developers are not so good at, naming things. So let's see if we can use Gen AI to simplify this particular code. So again, I just go and click on the auto refactor button and I get a proposal back. And by the way, yeah, you see that here on the top, that's like the outcome of our fact-checking model. So here you can see that this refactoring actually solves the problem, it improves the code health, and it also seems to preserve the semantics of the code. So if I'm happy with this solution, I can just apply it. So let's see what the AI actually did. So what it did now was that it took that complex conditional and it extracted it into a new function, and then it put a name on top of that function. So this is something that looks ridiculously simple, and it is. I'm going to stay around for questions afterwards, I promise. So this is a simple change, but it completely changes the context. Because now I have a label on top of that complex conditional, which makes it so much easier to reason about the problem we're trying to solve. So once we have built that solution, we benchmarked it and we compared it to an out-of-the-box AI model. In this case, we choose to go with GPT 3.5. We also did the same study for GPT 4, which basically performs at the same level, slightly better, but that's being compensated for the AI being almost an order of magnitude slower and more expensive. So we didn't find that it was a viable solution. And what you see here is that in the first row, you see the performance of GPT 3.5. And in the bottom row, you see the performance, the correctness you can achieve with a fact-checking model on top of the AI. And what we see here is that we basically managed to deliver correct refactorings in 97–98% of the cases. And of course, you might wonder, I mean, 98% correct refactorings, does that mean that if I ask the AI to refactor 100 code smells, I'm going to introduce 2 bugs? Yes, actually. That's what it means. But let me remind you that that performance is actually better than what a human would achieve. So by using a fact-checking model on top of Gen AI, we can actually elevate AI-assisted coding to the level of human performance. Now, the last thing I want to talk about is how often would you like to do this? How often would you like to take code and refactor it? So just a couple of months ago, we did a new research study, a follow-up to the Code Red paper, that will help us motivate the need for refactorings. So basically, the code health metric that I talked about, under the hood, it's much, much more granular. It doesn't just have 3 categories. It's actually a scale that goes from 10.0, which means perfectly green code, all the way down to 1, which is some of the worst code you can ever imagine, right? So what we did was that we simply calculated a statistical model that will let us predict what's the value creation, added value creation or loss to the business if we improve or lower the code health. And value creation is what you see on the y-axis. And value creation is simply a composite measurement where we combine speed, velocity, we can ship feature faster with defect reduction, right? So that's what I mean with value creation, the things we looked at in the diagrams before. And this allows us to reason about cost and risk. So let's say that you try this out on your own code base, and you find that we're doing a really, really good job. We have a particular module and we're in the green zone. Maybe we're at a code health of 9. So everyone is happy. Does that mean you can sleep well at night? No, you cannot, because if you look at that curve, you see it's an S-curve, right? It's a non-linear relationship. So maybe something happens, and maybe that something is a deadline, and maybe you compromise code quality a little bit to meet that deadline. And now you found yourself that you've slipped a little bit. And it looks innocent on the curve, but if we actually look at the number, we see that just that minor slip results in a minus 45% value loss to the business, right? That means you're going to be slower and you're going to introduce more defects the next time we work on that code. So based on that code quality research, I like to conclude that the right time to refactor is now. And what I want to show you in this presentation is that now in the age of AI, code quality is going to be more important than ever. And in particular, I think we're going to have to shift our focus from writing code to become better and better at comprehending code, because that's going to be a real challenge in the years ahead. And I'd also like to remark here that as AI might accelerate the creation of new code, we also have to be careful, because as we have seen throughout the presentation, acceleration on its own, it's just not useful if it's driving our projects into this brick wall of technical debt, right? On the other hand, if we take AI and also focus it on this big win, the 70% that we do of understanding existing code, then we can reach dramatic results. And I like to think that optimizing code for understanding is where the big win is, because that is the dominant human-intensive aspect. So I'm going to hang around for the rest of the conference. I'm going to be here today and tomorrow, the whole day, and I'll be more than happy to discuss these things with you. Before I leave you, I would like to give you a couple of references. So if you want to read more about code quality, then the first paper is for you. The second paper is the refactoring study, where you have all this benchmarking data on the different AI services. And if you want to try this on your own code, then there's a free implementation available of this AI refactoring tool that does the fact checking. You can just go to codescene.com/AI and sign up, and you will get access to it for free. It's going to be a freemium version. And of course, if you're curious to know what your own code health is, then please have a look at CodeScene and consider to support that. You can try it out for free on your code and get to know your code health. And finally, a little bit of self-advertisement. I think that's perfectly fine on a Thursday afternoon, isn't it? Yeah, it is. If you want to know more about code quality, software development, and refactoring in general, then you can probably do worse than checking out my new book, Your Code is Crime Scene, which just came out in our second edition. And with that said, I'd like to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thank you.
Nice one.